All right, we'll get started. So last time we were talking about the cap theorem, so we'll start with a quick review of that. Just 2 minutes, talk to each other, see if you can identify what the trade-offs are here. So what are you really being asked to do or to handle? I think that's one of the problems with the cap theorem. It looks really good from a distance, but when you sit down and you say, what is it really telling us? How is it really guiding us? I think that's where it becomes harder to understand. Fix it. All right. What did you come up with? Nothing?
When you said network partitions, like they do happen because they're on old network.
We don't really get to control that part, do we?
So you pick one of the other two to emphasize.
Right. So usually when these kinds of triads are put together, it's the two. But the point in this one is, and that's why I say it doesn't fit. It tries to appeal to that same intuition, but it doesn't quite fit because you don't get to control when the partition happens. I mean, I actually have a complete simulation now of building Paxos with Mars in it, where it's really kind of cool because what you find out is that if you organize your forums correctly, Mars never actually loses access to the database. And what I liked about it is that it teaches something that you don't normally see when you're looking at Paxos up close, and that is Paxos doesn't promise that everybody's reading the same view of the data. It's only promising that you read a linearized view of the data. And so for the 2 weeks that Mars is out of contact with the Earth, all the little Martian apps can keep reading from the database just fine. They're just reading data from 2 weeks ago. but they're reading it in the right order. And I thought that was actually kind of cool. And so that's kind of an extreme example of a partition. That's why I really like that. Bless you. So the ones that we get to care about are the correctness, consistency, and the availability. Those are really what we're balancing off against each other. And what the people who build these systems will tell you is they're going to solve both of them. And the reality is you can't. But what we can do is we can keep pushing that closer and closer together. You know what the interesting thing about the my Martian model was, where we had data centers on Earth, we had data centers in low Earth orbit, we had data centers on the Moon and on Mars. The consensus time in the low Earth orbit is actually faster than it is on Earth. And the reason is that when you communicate with a satellite, you do have a delay, but it's actually a fixed delay. And that delay is the speed of light. When you do it through cables and optical fibers, you actually have higher latency. So communicating from the western side of North America to Europe has a 60 millisecond latency, no matter what you do. And that's actually slower than what you can get to a satellite. This is kind of fun to actually experiment with that. So maybe I'll annoy you guys with it at some point. So a lot of this isn't really the issue when everything is working. And that is always the problem when you try to reason about distributed systems, is that most of the time things are working, and in that instance you're going to have everything that you want. The only time that you have to compromise here, well, aside from crappy implementations, the only time you really have to compromise here is when the partition occurs. Which one are you going to favor? Consistency or availability? Now, the interesting thing about that Martian example was it has availability on Mars. As it turns out, because of the way that the forum is constructed, it has availability and writability on Earth. Writes from Mars are slow. Not much you can do about that. Writes from Earth, they're fast, because you only have to get agreement from the earthbound tier. So, I mentioned this before, this is Google Spanner we're going to be talking about. Did anyone read that paper? It's actually a really good paper, because it's a more engineering-y paper than an academic-y paper. And that's not uncommon in systems. Systems papers often are, we built this thing and this is what we learned. And that's a different read than, here, we're going to build this theoretical model of what it takes to build a data center on Mars that doesn't actually interfere with Earth or anything in between, but still actually works correctly and provides strong consistency guarantees, because I didn't go out and build a Martian data center. I simulated a Martian data center. If the data centers are 100 milliseconds apart and a user in Tokyo writes and a user in London reads 50 milliseconds after the write, what do they see? In an eventually consistent model, the user in London might see the old value. If you have strong consistency, the user will see the write, but what's the cost of that? See, this is where those acceptors getting the messages makes a difference. When an acceptor knows that a value is in play, actually, sorry, it's the learners that know the value is in play, usually because they're sitting next to an acceptor. When the learner knows that the value is in play because there's an outstanding proposal for it, the learner has to block the read on that value until that has concluded. But here's the trick in a partition. The learner doesn't know, because nobody in its partition knows that there is an outstanding write on the other side of the partition. So now what we have is the network packet delay issue. That's what's really interesting about that, is that network delay allowed. If I read, I get the last value. If I insist on making sure that I'm always reading the most up-to-date value, I'm never going to make any forward progress. Because anyone proposing is going to block me from reading, because I don't know what's in that window. That's kind of how Google gets out of this conundrum. They say, here's how big the window is. We'll make sure we wait before we send our packet, so we're outside that window, so anything else that was inbound, we know we'll have seen. So, I don't know, that was like 2 months ago, right? This is lecture 19, so 10, yeah, that's 5 weeks ago. So 5 weeks ago, I'm sure you remember it really well, because I remember it, like, not at all. We put the nodes in a grid, and then we numbered the nodes, and we used that to reason about what the communications look like, what our quorums look like. As we matured through that, we said we might actually want asymmetric quorums. And the example that I've been using today, which is the Martian example, is in fact the extreme of that. It is a very asymmetric quorum. If I want an agreement, everybody on Earth has to agree to it for Earth to decide. That gives us the intersection property. But if I want to write from Mars, it means I have to get everybody on Mars to agree, and then everyone in each tier below me to agree. So I have to get the Moon, low Earth orbit, and Earth. And that's where Mars experiences long delays. It's slow to propose writes from Mars. But it works. And it works correctly. We get linearized order of our operations. But let's look at Google, because what they're really doing is building an actual system that makes trade-offs that work within their usage environment, which is data centers scattered around the Earth. So we're just looking at the Earth tier now. How are we going to make this work within the Earth tier? If machines are inside of the same data center, then the latency is about a millisecond. If it's on the same rack, it's not milliseconds, it's sub-milliseconds, microseconds. And the reason for that is the way that all data centers are built these days is, I think I mentioned this before, they build racks. And the racks are built off-site. They're not built in place now. I mean, in the CS department, maybe they actually have, well, I know, we have computers around the CS department that are racks that individual groups control. And they're done the old-fashioned way, which is people actually put the hardware in them, and they wire the back, and they make sure that it plugs into the power supply. But at data center scale, it's all a single unit. They bring it in with a forklift. They put it into place. It has massive power connectors. It's got network connectors. It plugs all of these things into there. It's all maximally set up for cooling, because the single biggest factor is that everything they run generates heat, and that heat has to be moved out of the data center, or otherwise the data center won't run very long. How many of you have a GPU? Does anybody know what the rough approximate max temperature of a GPU is? Sorry?
Mine went up to 97 degrees.
Yeah, that's kind of at the end of the range, right? 80 to 100. 100 is generally high. Do you know what a GPU normally does, or a CPU for all that matter, when it starts hitting its high-end number, its high-end thermal number? Because they all have thermal monitors in them. It throttles. It literally slows down the machine. I've worked with processors that have vectors do this big time, but like regular CPUs, Intel Xeon CPUs, that have internally throttling that happens because when you're doing vector multiplication, it heats the chip up. So they have special instructions for these vector multiplication operations, but then they have to slow them down because it will cause the chip to melt. You're sitting there laughing, but it's true. Heat is a huge problem there. If you want to remove that heat, what you end up doing is crazy things like putting air conditioners on your CPUs. It's called phase cooling is the official term for it. But when you look at it, you're going, wait a minute, it's just an air conditioner on the CPU. And the CPU is quite happy. I have a GPU at home, a 4090, that is water cooled. I don't think I've ever managed to get it above 45 degrees, which for a GPU is like in the freezer. It means that it's going to live longer. But in a data center, racks, lots of heat, lots of problems, but the units themselves are built with redundancy in them. So they can handle certain kinds of failures. They have disk arrays, they've got ECC memory, sometimes you can have multi-bit ECC memory. ECC means error correcting code. It literally means that if we read from the RAM and one of the bits is wrong, we can fix it. The cheap kind of memory is called parity. In parity memory, we can detect a single bit error. And we tell the operating system, oh, sorry, that memory didn't work well. And the OS will try to recover from it if it's like in basically read-only memory. Like something you loaded off disk, for example. It will move it, and it'll mark that region of memory as unusable. Well, until next time you reboot, because why remember these things? But ECC memory will correct a single bit and detect a double bit. And there are even more extreme examples of that. When you start actually building things for low Earth orbit or anything that's going to be in space, you use multi-bit correcting logic. So it's really built, the hardware is really built to withstand a whole class of failures that we're not even really thinking about. They keep saying there's lots of things that can go wrong, but how many of you sat there and said, oh, well, of course, that means the memory could give me back the wrong answer? I've actually debugged single-bit errors before. And the weirdest part about single-bit errors in code is that they can run for years and no one sees them. Because almost never does it actually cause someone to fail catastrophically. There's a lot of bits, most of which are never even accessed or used or relied upon. But when they break, boom, they become a crisis. So these data centers are huge. They are refrigerated. They generally don't allow people in them because, of course, you want to keep the environment as controlled and clear and clean as possible, and people bring in dirt. Dark, because there's no reason to run lights. They generate heat. You have to pump the heat out. And so the way it works now is we have what's called a top-of-rack switch. And then we'll have, sometimes we have disaggregated memory, so we have just memory by itself. And then we have GPUs and CPUs, and sometimes FPGAs or other specialized hardware on them. But it's just one big unit. And the time it takes to communicate from one piece of that unit through the top-of-rack switch to some other part of that unit, of that same rack, is slower than bus speed, but not a lot. Network devices can now run 800 megabits per second. That's the last time I checked. My guess is it's at 1.6 terabits per second now. Those are bus speeds. They're not near bus speeds. Those are bus speeds. Those are the same speed that you see from a CPU on your laptop talking to its own memory. So now the only thing that controls that is literally the speed at which we can transmit that information over whatever we're using. It's fiber optic cables or it's copper wires. Anybody ever heard of Grace Hopper? So Grace Hopper, she was a admiral in the U.S. Navy, and she was very heavily involved in early computerization. And she used to carry around a piece of wire that was 11 inches, which is about 27.5 centimeters long. And she said that's a nanosecond. That's literally how long a piece of wire has to be in order for an electron to travel that distance in 1 nanosecond. So it's a nice visceral example. Wow. And I thought it was really cool that she actually carried a piece of wire with her and said, this is a nanosecond. So these are very small. I mean, a nanosecond is way smaller than a microsecond, or microsecond is way smaller than a millisecond. So the speeds are very high, the latencies are really low, and almost all of the problems we're talking about in terms of sequencing and ordering and whatnot don't occur, because when you're sitting in the same rack, you are fate sharing. The power doesn't go out for one piece of it normally and not another piece. It goes all at once or not at all. And so that also means that when you're solving these things for an intra-data center situation, intra-rack, simplest, intra-data center, that gets more complicated. Inter-data center is where it starts to get interesting because now the latencies matter. We went from 1 millisecond to 40 milliseconds from coast to coast. And I think you're lucky if you get 40 milliseconds, to be honest. And then from the west coast here to Europe is somewhere in the 100 millisecond range. I have an EU account, World of Warcraft, and when I play, I see about 150 millisecond round trip time. So that's 75 milliseconds each way. But if I'm in the east, I see half that. I see less than half that. I see like 60 to 70 milliseconds round trip time. So it's real, it's measurable, it actually makes a difference. And it's the difference between those latencies that becomes harder for us to reason about. So at some point, quorum design becomes latency engineering. How am I going to deal with these increasingly large latencies? That's why I like the Martian example, is because it suddenly makes it really visible what it is that Paxos is buying you and what it's giving up. Paxos buys you strong consistency, but linear consistency. Well, what you give up in exchange is you don't actually have simultaneity, and you give up a lot of liveness when there's a partition. You give up liveness from one of the partitions. At most, one of the partitions still has liveness. All of the others will have no liveness. So when we're doing quorum design and we're doing it across geographic boundaries, we start thinking about how that latency begins to affect us. So, in the EU, we can do a local read. We can get a read quorum across our tier. And we can organize our quorums, our quora, so that we can just read from our local tier. Because if we read from everything in our local tier, and we require at least one node in every other tier for a quorum, that works. We know that we're going to intersect. But a write quorum now requires at least one node from each of those tiers, each one of those layers. And that means you've got 2 WAN hops. Now you can do those in parallel, so it's not the sum of them unless you really implement it badly. Hey, I'll send a 100 millisecond packet first, and then I'll send a 40 millisecond packet second. No, you send them both at the same time, and you wait till you get responses from both of them. So it's max up 100 milliseconds. So since we always will have a non-empty intersection, we actually do have a quorum. That was the requirement we had for a quorum. So we can do reads entirely intra-data center as long as we require that our write quorum always has to span all 3 tiers. So this gives us a couple of different strategies. One strategy is that we can actually have local reads with durable writes that are slow. So the read quorum is all the nodes in one data center. That's fast. It doesn't require a wide area network. The write quorum is one node per data center, but that's slow because all of the WAN links are involved. Now that's where it becomes interesting, because now what we're saying is if write is uncommon and read is common, That's what we would probably do. But suppose it was the opposite. Suppose this was a write mostly, read occasionally model. Like it's telemetry log. You're not looking at the telemetry log all the time, so you can make the read slow. In this case, what we do is we do the opposite. We say our write quorum is all the nodes in one data center. No WANs involved, it's fast. If we go to read this, though, we have to read across all of these quorum. And this is what's kind of cool, is that this is the trade-off. This is the cap trade-off here. In the first strategy, we lose the ability to write if any one of the nodes, any one of the tiers goes down. We lose the ability to read in strategy 2, which is probably not the most intuitively obvious choice. But again, if you're write heavy, not read heavy, you're going to choose strategy 2. So it's not about the quorum size, it's actually the latency profile that drove the decisions in these strategies. And that's what happens in real, actual development and deployments. And when you build these things, you start thinking about the latency and the effect that latency has on your performance. Because it's easy to sit down and to write a distributed database, because I think half the class is doing that for their capstone, because it's easy. You're doing something crazier, right?
Yeah, super crazy. Raft on Paxos.
Raft on Paxos?
That's a thing.
Interesting. This is going to be an interesting one. Raft on Paxos. I'm trying to figure out what problem you're solving, aside from making it really complicated. But that's good. I don't have to think about that. They have to. They have to convince me. All right, so let's do a quick sanity check. You have your system servers. Your system serves users in both the EU and the US. The workload is 80% reads from the EU, 20% writes from the US. How you can configure your quorums? We'll do 3 minutes. You don't have to do it in pairs. I don't really care, but. And of course, this is good practice because when you're actually in the real world, you'll find that managers like to walk into your office and ask you questions like this and expect you to have answers like in 3 minutes or less. Okay, we're going to spend $1 billion on this. You need to tell us in 3 minutes how to do it. It's not quite that bad, but sometimes it feels that way.
My thought process is like, if you have 2 nodes from EU and US, that makes sense. But then like, the reason there's more EU and less US is just because the need to read more. I don't know, my intuition is the buffer just, and this thing I wasn't thinking about, what is that legacy anymore? DCs or what does it generate?
It's interesting.
I was just thinking you maybe that's the reactor. But then you just need yeah, we need just one each DC for lights and full DC battery.
All right, what did you come up with? Kind of a hard problem, isn't it? Probably could have built this into a capsule. Anybody willing to throw out an idea there? Okay. Well, I'll tell you what Google would have done. Well, because it's what they did. So Google built this thing called Spanner. And it was a globally distributed, strongly consistent SQL database. And what they argued was that they had consistency, availability, and partition handling solved. But, as I said, it's one thing for the marketing people to tell you that it tastes better, and another thing to give them something to you that actually tastes better. I mean, how many of you have ever gone to purchase something, going, oh yeah, I'm really excited because of the advertising, and then you actually tried it and you were like, this was not what I expected. Right. Happens all the time. It happens in tech. How many times has a piece of tech been told that it's going to make your life perfect? And you get suckered into it. People are smiling at this because I know it happens, right? You get suckered into it and you go, okay, well that really looks cool because that TikTok influencer convinced me. And then you get it and you're like, this is crap. I could have just bought some cheap piece of junk off Temu because it was probably, purchased and shipped that way. It's not quite that bad. Spanner isn't that bad, but Google did in fact say, look, we can reason about this, and we can reason about the latencies, and we can make this work in a non-intuitive way, but make it function correctly. So what they actually had was almost like what you're describing. You were doing graph on Paxos. They did Paxos on Paxos. So they had data. It's sharded across Paxos groups. What that means is that part of the database is here, and that database, this piece that's here, is replicated itself through Paxos. Great. And then on top of that, they had a replication of the shards themselves into other data centers. So we have geo replication to protect us. We have local replication to protect us. And then anytime you had to perform an operation between shards, you use two-phase commit. Now, you don't have to do the last DS Labs project, but that is, in a nutshell, what the DS Labs project does. It takes sharded, replicated Paxos, sharded replicated Paxos, and it puts a two-phase commit layer on top of it to allow you to redistribute things in the shards. Now, I mentioned before, the benefit of using a key value store, and the reason it's such a common model is it shards. It's very easy to say, all of the keys that match this pattern go here, all of the keys that match this pattern go here. It's a static configuration. You don't need anything very complicated to do that at all. But of course, we're distributed systems people. We like to complicate things. So when they start building more complicated sharding systems, they build them so they're overlapping. So this is 40%. This is 40%. And this is 40%. Why would you do that? Well, because now you have an extra level of redundancy, but it's not complete redundancy. And you can do some load balancing. And there are reasons that people do that, but it does complicate things. However, key value stores are really easy to do decomposition. And from the client's perspective, they don't care. They're called get and put. And they don't care where the get or put gets satisfied. So it's a routing layer that you put that's transparent in the middle that says, oh, that key, it goes over here. That key goes over to this other shard. And that's why you see this structure. Suppose that you actually included as part of your key the geolocation. Now you shard on the geolocation. Okay. So this is one of the reasons why you might want to do this, because this allows you to have US and European data centers and Asian data centers, and it turns out there's not a lot in South America, or almost none in Africa, data centers. They're much smaller, unfortunately. But these data centers can have a geotag as part of the key. And the client doesn't care. The client's just asking, he just gives you a number, and you just interpret that number with whatever structure you put into it, and it's transparent to you. This now gives you a way of doing geosorting through the sharding model that you probably didn't think about until I mentioned it. I don't know, anybody sit there and think, wow, I could put geotags in my keys. But once you see it, you're like, oh, okay, that makes perfect sense, especially when you have a sharding model. It's just routing data. Here's where it becomes interesting. The external consistency is a real-time ordering of transactions, and this is what I've mentioned before. They kind of cheesed it. Because what they did was they said, we're just going to delay sending messages to ensure that they're in a linearized order. All right, so every shard is a Paxos group replicated across the data centers within that particular region. Each shard has multi-Paxos for ordering, so they're doing a leader election because multi-Paxos makes a lot of sense when a stable leader is easy to achieve. Multi-Paxos actually doesn't work very well when the leader's not stable. If you are building a swarm of drones that are being used in a conflict someplace, you won't use multi-Paxos because all you gotta do is kill the leader and then they force an election. You might as well just simply leave it as, hey, whoever wants to do something, propose it and make a decision. Not that we would build swarms of drones and use them in military situations or anything. Inside the shard, we're using multi-Paxos across the shards in order to guarantee that our changes are not visible. We use two-phase commit because Paxos is about replicating data. Two-phase commit is about maintaining consistency against dissimilar data sources. They're solving different problems. So, 6 weeks ago, we talked about using quorum for visibility. Ballots in the quorum gave us ordering of the proposals. Ballots are logical. They don't order real-world events. Yes?
Sorry, I'm still very confused about the sharding.
Okay.
Like how they shard the data. Like each shard, like
Okay,
is
so
Paxos.
so everything everything that you store in a key value database,
Yeah.
in a KV store, has a key. And the key is nothing more than a string, right? Because that's all a key is. It's just a string. Whether it's a binary string or a hexadecimal string or whatever you want to represent it as, we always think of it as a string. So now what you can say is all of the strings with this bit on the low bit as 0 go to this shard. All the bits with 1, the low bit is 1, go to this shard. It's literally just doing a simple mask operation on the key to route it to the correct shard. My observation about geolocation information is if part of the key represents a geolocation, you can say, oh, this is the European part of the key. We'll send that over to the European data centers. And then they can decide where to send it from there. So that's the fun part about sharding. We can shard, and then below that we can shard again. But the sharding, hopefully, if we've picked our sharding protocols correctly, will lead to fairly uniform distribution. The danger, the risk is that when our workloads are not uniform, and they seldom are, we can get hotspots. So we can have shards that are very busy and shards that are not so busy. I talked about the overlapping shard thing. That's actually one reason why sometimes they do overlapping shards. It allows you to have distribution of hotspots. And it tends to create a more uniform, normal distribution. Otherwise, if you pick your shards bad, you put all the hot data in one shard, all the requests and operations go against that one shard, and you might as well have just left it all in one big pool.
Sounds very similar to hashing.
It is hashing. That's exactly what it is. I mean, a key value store is nothing more than a hash map.
Oh, I see.
The key is literally the hash value. Except that we don't know how the hash value is generated, right? You're probably sitting there thinking, oh, MD5, SHA-1, SHA-2, SHA-3. Those are all Blaze. These are all cryptographic hashes. And so they give very good randomness relative to the baseline data. But hashes don't have to actually be cryptographic. They can actually be structural. UUIDs are a really good example of that. Anybody know what a UUID is? They're used everywhere. I actually was at the meeting where they were deciding on the actual format of the UUID in, I don't know, 1989, 1990, somewhere in that time period. I think it was 89, in Boston, Massachusetts. And I still vaguely recall, I probably wasn't much older than you guys are now, I vaguely recall them talking about the structure of a UUID. And part of it was the Ethernet address of the machine where you generated it, because they wanted it to be separated. So that was a way of separating it. And then another part is a timestamp, because that timestamp limits how many UUIDs you can generate on a single machine in a period of time. It kind of ties into the spanner idea. Interesting. And so they were arguing about how many bits we want here, because the clock is finite size, and therefore it rolls over. Some of you were born before the year 2000. Before the year 2000, there was this big panic because people stored dates as 2 digits, and they were all worried about the fact that when it came to be 2000, the computers were all going to melt down and stop working because they were going to go back to 0. And the world didn't actually end. Some things broke, but the world didn't actually end. And this clock rollover issue happens all the time. The GPS satellites actually have a fairly small clock, and it's rolled over like 5 times now. I'm making that number up. It could be 6 or 4 or 10. I don't actually know, but I know it has rolled over. The UUID time, or the UUID type 1 time stamp, my recollection is it rolls over in the year 3049. So, you don't worry about it. Those values can be whatever you want. That's why it's a key value store. The key can be a hash, often is a hash, but doesn't have to be. It can be a structured hash value, where part of it's a hash and part of it is some sort of a routing value. How many of you have heard of IPv6? You've all taken 317. Hopefully they talked about IPv6. Oh yeah, there's this protocol that we invented in the 1990s that we're just kind of getting around to adopt now in the mid-2020s. That happened to have been co-invented by a UBC grad. All right, did that answer your question? It was a great question, by the way, thank you. That was really good. All right, so let's look at the ordering problem here. So we've been talking about logical ordering, not chronological ordering. And I kind of live this on a regular basis because I realize that I deal with AI a fair bit. Every single time I have an interaction with Claude or ChatGPT or Gemini, their clock is a Lamport clock. It's literally a sequence number. This is message 1, this is message 3, this is message 5, because they get to do the even numbers, you get the odd ones. That's their clock. Your clock is, and the way I usually describe it is it's an accidental celestial clock measuring based upon the rotation of a tiny grain of matter surrounding that orbits a nuclear power plant. And if you think about it, that's what our clocks are based on, right? They're based on the rotation of the Earth. They're based upon the rotation of the Earth around the sun. I don't know that it's any more real than a Lamport clock, honestly, but that's the clock we live with. How do I reconcile these two clocks? And that helps me back and forth because I say, okay, you have a logical clock, I have a physical clock. They're trying to do the same thing, but they're not the same measure of time. Paxos doesn't give us physical clock time, it gives us logical clock time. It gives us a linear order of events, a logical clock order of events. But external consistency requires that if we have a transaction that commits before another transaction starts in our real time, then the commit timestamp on that transaction has to be less than the commit timestamp of transaction 2's. Now notice this is the commit timestamp, but this was commit versus start. And that is the key here. I just need to know that T1 happened before T2. I'm not saying that T1, let's see, T1 commits before T2 starts. Right, I am saying that. If T1 finishes before T2 starts. So what we have is this overlap time. It's the time in the middle that we don't really know. And that's the point of Paxos. It says these things happened in this linearized order. That's all it's doing. It's just simply pushing everything through a funnel and saying it comes out in sequence. A sequence. But inside, when they're in the funnel, we don't actually know what the sequence is going to be. So Lamport clocks can't actually give us this guarantee with a real timestamp. They're capturing causality. They're giving us this linearized consistency. But what Google wanted was to use actual clocks and make them have the property that we needed with respect to consistency. So they said, we're going to build this thing called true time. And true time is a bounded range. It's not a single value, it's a range of values. It says the time is somewhere between this point and this point. And that window is going to be a measure of the latency that the system is experiencing. So the way they did this was they built GPS receivers and they put atomic clocks in every single data center. I think at the time, I'm pretty sure in their paper they said it was like $500,000 US per data center to do this. And now you can buy these things for like $2,000 US. Probably would still cost you $10,000 to get everything put in and wired up, but you can get GPS clocks. They have two independent time references, so that if one of them fails, like you get a really bad thunderstorm or something, you can't talk to the GPS satellites, then that will work. And they keep the interval, the epsilon value. Gotta love the mathematician sneaking in there. Oh, we'll put an epsilon in there. That bound around the uncertainty time. And for Google, it was about up to 7 milliseconds, which is pretty small. So 3.5 milliseconds before, 3.5 milliseconds after. So that's what our timestamp now looks like. It's a bounded timestamp value. And essentially, this is a measurement of how uncertain the system is about what's going on. And this is kind of the reverse of what Lamport did, right? Where we're measuring clock time, not Lamport clock time. By bounding it in this way, we have the earliest and latest time, and then we have some epsilon before or after. Okay, so they're going to set epsilon as being the whole, half the span, not the whole span. Doesn't matter, it's the same. The GPS receiver synchronizes across the data centers, so that's how we're keeping the time synchronized. The atomic clock's bound how much drift there is between GPS fixes, so if there's been a while since we've been able to talk to GPS satellites and sync back up. And as I'm sitting here talking about this, I'm going, but what is this going to do for Mars? Because maybe you aren't aware, but Mars doesn't have exactly the same time as Earth, because relativity affects Mars. GPS satellites themselves are actually subject to relativistic effects. But all the GPS receivers and all the satellites, they all know how to correct for the time so that they know what the terrestrial time is. So in essence, what's kind of cool about that is what Google did was what the GPS satellites are doing anyway. They know that they're within some time boundary, and you read multiple GPS satellites, and you can use them to correlate what time it is. Because you're going to know what the difference is. You can use that difference to infer where you are in that level of uncertainty. So clocks give you a specific point in time. But what they're lying about, or they're not being truthful about, is that there's a certain level of imprecision for that specific point in time. So they're giving you something very precise that is, in fact, maybe not as precise as you'd imagine. They're not giving you a plus or minus. They're not giving you error bars. I think that's the right way to think of it. There's no error bars there. True time gives you the error bars. It says it's somewhere between 10 o'clock 0.001 and 10 o'clock 0.005. And this is now our guarantee, is that we're within that interval. Now, guarantee is probably a little stronger than I would have personally used myself, but this is the way that Google presented it. Let's just say with high likelihood, it's within that range. 5 nines or 6 nines or something. So you can't eliminate the uncertainty in physical clocks, but you can actually establish an epsilon bound on it. And that's enough for us to then say, okay, now we can fix our linear ordering, because what we can do is we can say, when the transaction gets the lock and it does its work, it picks its commit timestamp, and it waits until the time now is greater than the earliest time could have been. And then it releases its locks and it reports the commit. So the wait here is between this 2 and 14 milliseconds, and Spanner thus trades latency. It increases latency by up to 14 milliseconds, but gives you a real-time ordering guarantee. And this is a little weird. I mean, there's no doubt about it. You're like, wait a minute. So you record the decision because you've committed, but you don't tell anybody, and just not telling them is enough to give you the linear ordering. That is definitely not intuitively obvious. Why does it work? Okay, because when T1 does its work, it gets to its commit point, it waits, and then it sends the message that says I've committed. T2 does its work, does the same thing. Now notice there's a small gap here. The point is that this gap plus this gap, even if it has happened concurrently, that commit will become visible before T2 since it's commit. And that's what we're trying to guarantee. So now we've given an ordering to these things. Because they start at different times. It's really about controlling the visibility of the commit itself. Yeah.
But this is happening like within each shard, right? It's not happening like across the different partitions, right?
It's happening across data centers. This was a cross data center protocol. So inside the data center, you're right. I think those times are in fact intra-data center, not inter-data center, because inter-data center, this is going to have much larger latencies. But remember too that we sharded down to the data center. So that 2 to 7 to 14 millisecond time frame intra-data center, then we're using multi-paxos above that. And then we would have a different layer where we're using a different time variation. Our time would become less precise. Because there's nothing here that says that it has to be 7 milliseconds. When we start doing this to Mars, it's going to be 14 weeks, or 14 days. I think it's 2 weeks is roughly the maximum. So you want to wait for 28 days before you send your commit message? That's a correctness versus liveness problem that happens as the latencies increase. If you don't do the commit wait, T1 picks their timestamp in DC East. T1 commits immediately without waiting. T2 started in DC West and picked its timestamp as 99. Even though it started later, it picked an earlier timestamp because the timestamps aren't exactly the same. And T2 commits. So then it looks like T1 committed before T2 in real time, but T2 says that it started before T1, because our timestamps are different. And that means that our timestamps are in the wrong order relative to our actual commits. But if we do the commit wait, T1 waits until it knows that this has to be a time in the past. And any clock elsewhere is going to be greater than S1 because it's outside of the uncertainty window. And now T2's timestamp has to be greater than S1 because it picked the range from 92 to 106. All right, so this is where things get hard. I think this is actually, the Google Spanner work is really interesting, but it also kind of requires that you work with a difficult, non-intuitive result. Why does delaying the message matter? So let's take 3 minutes to talk about this and see if. So what are you getting for this cost? What's the benefit of it? This complexity, and what would happen if you used Lamport clocks instead of the true time clocks? 3 minutes. All right. What did Spanner choose? Because that would define what they're getting. There were only two options. Now what? Sorry. There's one. Oh!
So it's true time.
True time, but what does that mean? I mean, it couldn't, so the point is that it can only choose, I mean, at some level you're right. So I want to tie it into what it really means here. In the CAP theorem, you can only choose consistency or availability over partition. So when a partition happens, you have to choose one or the other. So true time is choosing which one.
Availability.
Why?
Because it's faster.
Availability because it's faster. Is holding the message for 7 milliseconds before you send it, the commit message, is that faster or slower?
Slower is.
Okay. So true time actually is picking the slower path. And so why would it choose the slower path? What was the other option besides availability?
Strong consistency.
Right. That's actually what it's doing. It says, this is a SQL database, we need strong consistency because people are putting monetary transactions in this thing. That's exactly the case where you almost always want strong consistency. And you don't really care about strong consistency when you're building a distributed system for a bank. But then again, they might not like that. Oh, we gave out too much money. Sorry. There's a bug in the Paxos protocol. It was that wrapped over Paxos implementation that did it. Just kidding. So Spanner chose consistency always. So the way it does that is using this true time externalized consistency model where we're actually using clocks, but we're basically saying anything in this time range is fuzzy, so we'll wait until we're outside of the time range, and then it's not fuzzy anymore. It is partition tolerant. Paxos groups actually survive minority data center disconnects because that's what Paxos does. Paxos is inherently partition tolerant. Availability here, though, is what gets sacrificed, because a minority partition cannot serve writes. It will block and wait, because it cannot get a decision on a write. So all those writes get arbitrarily delayed. But that's fine. We're not sending commits back on writes that didn't actually happen. So that doesn't cause us any problems or issues here. Maybe that's the right way to think about it. You're basically saying that you don't tell anybody what happened until later, so the learners learn about it in a canonical order. I'm not sure I like that framing, but so in Lamport clocks, we had this causality order. If A happens before B, then the cause of A is earlier than the cause of B. If the cause of A is less than the cause of B, then, so we're doing the contrapositive, then cause of A, the causality of A is less than the causality of B doesn't mean that A happened before B. Right. Right. So the inverse is not true. That's a logical statement. If A implies B, does not mean B implies A implies B, does not mean B does not imply A. Not B implies not A. The contrapositive is always true, but the inverse is not always true. In true time, if T1 finishes before T2, if T1 finishes before T2 starts, then its starting time is strictly less than the starting time of T1's starting time is less than the starting time of T2. But that requires these physical clocks with bounded uncertainty, and the timestamp order is in fact what we define to be the real world order. Now, I find this kind of interesting because I did point out that we have all sorts of relativistic effects, and there are actually places on the Earth where time flows at slightly different rates, measurably different rates. And that's kind of like, okay, so in some ways, by building this true time thing, what we're doing is saying this is our clock, and we're constructing a monotonically increasing sequence. We're just doing it using GPS and some logical structuring, or logical ordering of what we're doing. Okay, I could buy that, but at that level I'm starting to say, why is this really different than a Lamport clock? Because a Lamport clock was just a monotonically increasing sequence as well. So we've just created a monotonically increasing sequence that happens to look like a timestamp. Does this give you an idea of how twisted the minds of the people who work on these things become? There's a reason that they get paid a lot of money to do this. So Lamport said physical clocks are unreliable, use logical ones. Google said make physical clocks reliable enough, then use them. They're solving different problems. I'd actually argue they're solving the same problem in different ways, but they said that they're solving different problems. I don't, we don't have time. We'll skip this. So let's just go to So what Spanner actually does is, so every shard is multi-paxos, so it has a leader. That's what makes it multi-paxos versus single decider paxos. The leader handles all the writes via phase 2, standard multi-paxos stable leader. The leader actually serves a read at timestamp without a quorum round trip. In other words, the leader becomes the sole arbiter of what time it is. Now that helps, right? Because now we know that everybody in that shard is getting the same timestamp. So this allows us to read snapshots as long as we're getting it from a replica that has been updated recently. But when we go across shards, we use two-phase commit because we're no longer replicating the same state. We're replicating different states. We are mutating different state across the data centers. And we use 2PC. TrueTime provides a commit timestamp that we can use with our 2PC, and then waiting for the commit ensures that this becomes externally consistent. So next lecture, lecture 20, Thursday, we'll actually talk about back into 2PC. And I feel like we're back to where we were like 8 weeks ago or 7 weeks ago, whenever I first talked about two-phase commit. It didn't go away. It's just that we had to deal with the replication side of things, and now we're back to, okay, now we're replicating it, and we need to move data around. We need to make decisions on dissimilar data stores that need to be consistent with each other. So, does anybody know what a SQL interface looks like? Anybody taking a database class? Use SQL? Okay, so I'm not reaching too far here. If you don't know SQL, you're lucky. I mean, as soon as you start learning how to do inner joins with multiple temporary tables, then your brain starts to melt down as much as it will, if not more, than talking about distributed systems. So underneath the SQL interface, we actually have this two-phase commit transaction layer that we're going to be talking about on Thursday. Today we talked about this TrueTime level. Then below that was the multi-Paxos layer, which is where we're doing this per shard replication, and that's what we spent all that time talking about in Paxos. And then finally, we actually have this local storage layer, which the whole idea behind the Petrov, and especially the Petrov readings, is to give you an idea of how that storage layer isn't just this dumb layer doing nothing. That storage layer itself is contributing to a lot of the complexities that we are building on top of to make all of this transparent and magically work for application writers, because as a systems person, I can tell you, application writers are wonderful people, but they're not very bright. The other thing that I've learned over the years is that application programmers have one goal in life, and that is to break systems. And so we are definitely trying to make our systems idiot-proof. And they're definitely trying to build better and better idiots. That's why we have AI now. Something for you to consider. What happens when the Spanner deployment says that the wait times have increased to 15 milliseconds? What went wrong? Where would you actually look for a problem like this? What itself is determining the size of that uncertainty level? This is a class of failures. I've talked about that the whole class. Is like, think about, what does the failure tell me? How am I going to recover from that? Well, now what I have is I have this interesting failure that's not disconnection, it's just getting slow, which in some ways can be worse than disconnection. Disconnection, I know something's broken. Slow, I just simply sit there and go, why are you so slow? And I start to hear.
Could it be like the call to the TrueTime external dependencies coming back too slowly?
Almost assuredly, it's either in how you're computing the time or it's in the network itself. Maybe somebody slipped in a new BGP protocol and suddenly your traffic is going through China. That actually has happened more than once. So BGP is a very strange protocol that routes traffic throughout the global internet, and people publish routes through it, and it has more than once gone through strange routes just by mistake, and it's kind of weird when it happens, and usually people start to notice because things get slower. When your traffic from here to Calgary is suddenly routing through Botswana, you might notice that it takes a little while to get there. And then again, you're on UBC Wi-Fi, so you probably won't notice because UBC Wi-Fi is already imposing a large delay. So what did we talk about? We talked about, let's see, we talked about quorum structure. We talked about wide area network latency being the dominant cost in almost any of these complex systems that we end up building on top of. It's easy to talk about Paxos and to kind of ignore the latency effect. But the moment the latency becomes a factor, it starts to really change the way that you think about how you solve the problem. That's why I like the Martian example. It's the extreme. It's so obvious that you can't use the standard techniques. It's suddenly you're forced to realize things that you were assuming that were true in that were true enough in the low latency environment, you could just ignore them. And in almost any kind of complex system that you build, there's always something like that. I could ignore that before because it didn't rise to the level that it broke things. But now I'm dealing with 14-week partition times. Now we can get around the 14-week partition time. We can actually put a relay satellite in a Lagrangian orbit. We could put a satellite in so we could send messages through the satellite to Mars and back, and then we wouldn't have that 14 days. In lesson 14, we talked about flexible Paxos and the asymmetric quorums that now we can start using for geographic tuning, for example. And that was one of the big contributions of Howard's work. And her work isn't that old. It's like 5 or 6 years. So this is fairly recent. So we're not studying ancient history at this point. We are really not very far off from the state of the art in what you will find in industry. True time was an interesting solution bounding clock uncertainty. Then we get commit weight, which trades latency for strong consistency. And Spanner's answer, which was strong consistency, but we sacrifice latency, but we're not sacrificing availability when we don't have a partition. So you can see we're going across this various spectrum, but it's looking at different aspects of the same problem from different angles. Next Thursday, we will talk about how Spanner used two-phase commit to build this kind of geo-replicated redistributable. Because that's the big thing, is that when you start out, you say, I'm going to put a key value store together. And the key value store gets busy because you're successful and people are using your key value store. And you say, how do I actually scale up my key value store? There's only two ways you can scale up in the data center. You can scale vertically, or you can scale horizontally. Almost everything we're talking about is around the horizontal scaling. The vertical scaling is you build a bigger computer, you put more memory in it, you put faster network cards in it. But that then starts to run into other issues like, okay, now I have a hunk of silicon that is generating so much heat, I can't remove it fast enough. If you think about it, the amount of heat that you can dissipate from a blob of silicon is based on the surface area, not the volume. So the volume goes up, the heat generated increases cubically, I think. And the surface area is only going up quadratically. So you can see fairly quickly, oh, I see why we can't actually build infinitely large computers, because the heat that's being generated outstrips our ability to pump it away. So we have to do horizontal scaling. And now we're back into distributed systems land. Because that's what we do in distributed systems. We solve these scaling problems by building lots of computers horizontally that are then coordinating and talking to each other. And then we come back and we say, we could probably pack these all in a smaller cube. And so then we end up with a vertical integration of horizontal components. And then we go and do that all over again. So we iterate. And this keeps you employed for the rest of your life. And that's it for today. I will see you on Thursday. And I would note that we are now, I think, is it 9 days? 9 days for the capstone, so if you haven't started it yet, you might want to start thinking about it before next Thursday. Not this Thursday, you can wait till next Thursday.
That's what we're going to do.
Hello.
So I've been working on the capstone, and so I wanted to ask just one question about Paxos.